Hey everybody, we're going to talk about section 2.8 from the book today. It's the derivative as a function. So we're going to look at how to view a derivative as a function and analyze differentiability of the functions. So this is not too big of a leap from looking at the derivatives at a particular point. So this should be pretty familiar and pretty quick for you to pick up. So after you watch this video, hopefully you'll be able to do some of the homework problems from this section in the book. So recall in section 2.7, we were finding the derivatives of a function at a fixed number we called a by using a couple of different limits here. And we looked at this limit first of all, which was the limit as x goes to a of f of x minus f of a all over x minus a, okay? And we also said we can also look at a different limit that gives us the same result. So, and that limit was the limit as h goes to 0 of the expression f of a plus h minus f of a all over h, okay? Now, the only difference here is we're going to look at this as a function, and we're going to call that f of x, instead of at a point f of a. All right? So let's just take a look at an example real quick here. And here's a function, a fairly simple function, x cubed minus x. And we're going to use our definition of a derivative to find the formula for f prime of x, which is our derivative function. So remember, our derivative function f prime of x is the limit as h goes to 0 of f of, now we're going to call this x plus h now, instead of a plus h, because we're looking as for a function, so for x in general here, minus f of x all over h, okay? So we're just going to use that particular limit. So this is the limit as h goes to 0 of, well, f of x plus h becomes x plus h cubed minus x plus h, and then we need to subtract off the f of x, so we subtract x cubed minus x, and we put all of that over h. Now, this simplifies a little bit when we cube this function. Up here we want to take x plus h cubed, so we have the limit as h goes to 0. So x plus h cubed is x cubed plus 3x squared h plus 3xh squared plus h cubed. Now you should have learned that from the Pascal's triangle or from binomial expansion, and then this just becomes minus x minus h. And then let's subtract off that x cubed, and this minus minus, don't forget that, becomes a plus x, and then this is all over h, okay? Now, as we've noticed before, a lot of this stuff cancels out, so the x cubed is going to cancel with this x cubed over here, and then the minus x and the plus x cancel. And notice everything left in our expression has an h in it. So let's look at this limit again as h goes to 0. I'm going to factor that h out, so this just becomes h times 3x squared plus 3xh plus h squared minus 1 all over h, which cancels here. So really, we're just looking at the limit as h goes to 0 of the terms that remain, right? So this is 3x squared plus 3xh plus h squared minus 1, right? So now we can take the limit by direct substitution. So these two terms here are going to go to 0 because h is going to 0. So our derivative function, f prime of x, is equal to 3x squared minus 1. So it's the same thing that we did at a specific point, but now we're viewing this as a function. So this works, so we can find the derivative at any point on that function given this f prime of x, or our derivative function, which is 3x squared minus 1. So what I'd like you to do now is, if you haven't already started taking notes, try this function by using that same definition. Remember, f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Now, use that definition with this function and see if you can get the derivative function for this particular f of x. Okay, hopefully you had some success with that, so I'm going to move on here. Now, a key concept we have to talk about is some of the different notations that are used to describe the derivative function. So we've seen f prime of x. Also, we could use y prime if we're in equation notation. But some of this notation is called Leibniz notation because Leibniz was one of the co-inventors of calculus. He was doing some calculus at the same time Newton was, but he was in Germany and Newton was in Great Britain. So Leibniz used notation. Here's the first type. This is dy dx. Excuse me, dy dx. And all of these mean the same, so these are synonymous. Then you could also say d dx of f of x, okay? Or d, the capital D, of f of x. Those are all common notations that mean the derivative function. So if you see any of those notations, you should automatically link it back to our normal notation of f prime x, which denotes the derivative function. Now, here's a definition or a theorem. Some books refer to this as a theorem. A function is differentiable at a if f prime of a, or if the derivative exists. So it's differentiable on an open interval ab if it's differentiable at every number in the interval. So some functions are not differentiable because the derivative does not exist at a point or at a few different points for that function, or maybe not at all. So we want to take a look at one of the common functions that we've seen before, and that's absolute value, and see that something interesting happens around 0. So remember from pre-calculus, if you want to write the absolute value function as a piecewise function, we know that this is x as long as x is greater than or equal to 0, and opposite of x when x is less than 0. So we need to look at see what happens at 0. So we're going to use this definition and then look at our limits and see if we come up with the same thing, because we know something weird happens at 0 here, because this is the point in the domain where we get the split from the positive x to the opposite of x. So let's just look at that limit as h goes to 0. Oops, sorry about that little malfunction on the board here. As h goes to 0, and we'll use x first, okay? So f of x plus h minus f of x all over h in this top part, right, becomes the limit as h goes to 0. F of x plus h, of course, is just x plus h, and then we have a minus x for f of x, right, all over h, which becomes just h over h, which is 1, right? So that means our derivative, f prime of x, for that top part is 1, all right? Now, as you might have guessed already here, look what happens for the bottom piece here when we're opposite of x, when x is less than 0. We get limit as, oops, sorry about that, as h approaches 0 of x plus h, right, minus opposite of x, right? Okay. I'm sorry, we need a minus sign here on our x plus h because opposite, because our function is opposite of x. So we'd have opposite of x plus h minus negative x there, all over h. which gives us, well, the x is still canceled, right? But that's going to give us negative h over h, which is negative 1. So our derivative function, f prime of x, is negative 1 when x is less than 0. Well, those don't equal each other. So that means that we're not differentiable at 0. So this is not differentiable at 0. Now, here's another way to view this, why this is going on. If you recall the other day when we were talking about the tangent lines, we said when you zoom in on a curve, if it's a nice smooth curve, then when you zoom in at a point, that curve looks like a straight line when you zoom in close enough. Well, that doesn't happen for the absolute value function. This is a picture of the absolute value function on a standard viewing window, but look what happens when I start zooming in here. I'm just going to do a zoom in around the origin and look. Okay, now I'm at this window, I'm clear down to 0.2. Look, I'm getting smaller. Look at nothing is, I'm down to 0.05 now here. Look at my scale changing, look at my scale changing. But when I keep this centered, do you see where, look, I'm clear into 0.001 now here in the middle, right? And a 0.019 on my scale over here, right? Oops. So if I move that back over, it doesn't matter how far I zoom in or zoom out. Look at this, okay? Notice I still see that V. So it's not approximating a straight line there. Doesn't matter how far you zoom in or zoom out. So that just shows you that it is not differentiable right there at 0, 0, or at 0 in the domain. Okay, so that brings us to our next theorem here, which says if f is differentiable at a, then it is continuous at a. Now, here's a few cases graphically where differentiability fails. Now remember, we talked about smooth continuous curves. Notice this curve over here on the left, kind of like that absolute value function, that sharp corner does not work because if you zoom in there, once again, it's never going to approximate a curve there. Here's a discontinuity, so we're not differentiable at a there. And also, occasionally you have a vertical tangent. So at some places where there are vertical tangents, it's not differentiable. All right? Now, just remember, also, the converse of this is not a theorem, okay? So the converse of this is not always true, which would be if f is continuous at a, then it is differentiable at a. So don't make that mistake. This theorem only works in its forward implication. Okay, so the converse is not a theorem. All right. Now, we're going to look at higher derivatives next. So we're going to take a look at the function that we did earlier, that x cubed plus, or I'm sorry, minus x, and look at the second derivative, f prime prime x. Okay, if you recall, a little while ago, we just did f prime of x, all right? And we found out that that was equal to 3x squared minus 1. So if we're trying to find the second derivative, so we denote that with 2 primes, then we just use our definition and simplify again. So we're going to use that limit definition, but we're going to use this as our function now, okay? So we're taking the derivative of the derivative, in other words. So we end up with the limit as h goes to 0. Well, this would be 3 times x plus h squared minus 1, right? That's f of x plus h. And then minus f of x would be minus 3x squared minus 1, okay? All over h, right? Hopefully we're at the point now where we can buzz through here and do the algebra real quick. I'm just going to cut to the chase here. But what you end up with is this, when you simplify this, you end up with 6x, okay? So the second derivative is 6x. not sure why I had that in there twice, so just ignore that. That was the same problem, okay. So in general, the second derivative is just the rate of change of the rate of change. But the most familiar example is acceleration. So acceleration is the derivative of the velocity function, which is the derivative of the position function, okay? So here's an example of, here's the position function, and I just used t instead of x. So we knew that f prime of t, right, was from back up here, that was 3t squared minus 1, right? So this was 3t squared minus 1. And f prime prime of t was that 6t, okay? So that's the acceleration function. So after 4 seconds, well, that's the second derivative, which is acceleration of 4. So that's 6 times 4, which, whoops, got a little ahead of myself there. That's 6 times 4, which is 24. And then the units there would be meters per second squared, okay? Now, on this graph, we see the position function. That's the cubic one, right? We see the velocity function. That's the quadratic one. And then we see the acceleration function, which is the second derivative. So we see the function, the first derivative, and the second derivative, all graphed on one page there, okay? So that's a real common application for the second derivative. Okay, folks, so those are the main topics in section 2.8. So I think that'll get you enough to start on some problems tomorrow when you come to class. These were our goals for the derivatives section. So we've done this first one here where we've looked at the derivative graphically, numerically, and analytically. We've talked about the derivative as an instantaneous rate of change, which was the limit of the average rate of change, right? So in other words, it's the slope of the tangent line, which is the limit of the slopes of the secant lines. We've talked about differentiability and continuity briefly there in this section. We'll talk about it more in chapter 3. We've talked a little bit about vertical tangents. We'll see a little bit more about that in later on in section 2.8 and then again in chapter 3. We're going to be looking more in depth at the characteristics of functions, their derivatives, and their second derivatives. And of course, we're going to do much more with applied problems using velocity, speed, acceleration, and other applications of derivatives and higher derivatives, meaning second and third derivatives. So thanks. Go back and watch the video and try that again if you need to, but I think you should be able to come to class tomorrow ready to work on some problems.